Light field morphing is a technique for morphing 3D objects represented by light fields. Here are two light fields. The one on the left is real and the right is synthetic. You can see that the morphed object in the morphed light field retains the essential features of both input objects. Notice that the morphing takes place in 3D. In our system, the user starts by specifying features in the source and target light fields. Then the system warps the source and target light fields so that the user-specified features are aligned. Finally, the two warped light fields are blended to produce the morphed light field. There are two key issues in light field morphing: specifying features and handling the visibility changes. We have built an intuitive user interface for specifying features. The system uses the epipolar line to help the user mark a 3D feature point in two light field views. The user specifies a feature line by selecting two feature points. The user specifies a feature polygon by selecting a set of feature points in counterclockwise order. With our UI, specifying feature elements is fairly easy. From the user-specified feature polygons, we can construct the global visibility map. The global visibility map is the key to visibility processing. For each view, the global visibility map tells us which feature polygons are visible. We have also developed a array space warping technique to fill the holes caused by object shape change. Suppose we have two light fields L0 and L1. We want to warp L0 to L0.5. We get the feature polygons of L0.5 by interpolating L0 and L1. Notice that in this view of L0.5, the area highlighted in red corresponds to a hidden part of L0 in the same view. For existing image warping techniques, this area is in a hole. Ray space warping can fill this hole by taking rays from other views of L0. Here we show a view in which the area in red is fully visible. For each occluded ray, we use the nearest visible ray. The details are explained in the paper. Now we show some sample results. Our first example is a facial morphing in 3D. In this example, both light fields are synthetic data rendered from cyberware scans. Here is another example with a cat and bunny. The cat light field is acquired from a real furry cat toy. The cat's fur is very difficult to model with traditional graphics techniques. This example demonstrates morphing effects with significant occlusion, shape changes, and specular surfaces from two real light fields.
We have built a 3D scanning system for acquiring high-quality graphical models of objects that are impossible to scan with traditional scanners. Our system can acquire highly specular and fuzzy materials, such as fur and feathers. The hardware setup consists of a turntable, two plasma displays, an array of cameras, and a rotating array of directional lights. During scanning, the object is captured from various viewpoints by the camera array. The plasma monitors are used for multi-background matting to extract accurate object silhouettes. For each viewpoint, the light array can be rotated to capture the object under different illumination. The whole acquisition process is fully automated. We use the acquired silhouette images to construct a visual hull of the object. As can be seen in this image, the visual hull is only a rough approximation to the surface geometry. To capture fine silhouette detail, we map view-dependent opacity onto each surface point of the visual hull. We call this new shape representation the opacity hull. Finally, we map the captured images of the object onto the opacity hull. The view-dependent radiance at each surface point is called a surface light field. Here is another object that is difficult to scan with traditional methods, a small bonsai tree. We now show a series of photographs of real objects, followed by animations of the acquired models. Surface light fields show the object with the original fixed illumination used during scanning. To place objects into new environments with new illumination, we capture surface reflectance fields. In this animation, we show a model of a doll, rendered from new, arbitrary viewpoints and with new illumination. To place the object into a new environment, we illuminate it using a downsampled version of the illumination in the scene.
Light field mapping is a method for compression and rendering of surface light fields that takes full advantage of graphics hardware to display complex photorealistic scenes at interactive frame rates. The scene you are currently watching combines light field maps of a synthetic museum room and denser sculpture captured through 3D photography. The video sequence looks as if it was ray traced, yet what you see renders at interactive frame rates using images only. A surface light field is a four-dimensional function that completely defines the radiance of every point on the surface in every viewing direction. The first two parameters of the function describe the surface location. The last two parameters of the function describe the viewing direction of a given point on the surface. Surface light fields are ideal for representing physical objects scanned through 3D photography since they preserve the realistic properties of the original dataset. For example, the surface light field of Van Gogh's bust accurately portrays the metallic appearance of the sculpture and the intricate surface details. This scanned physical object has even more elaborate surface reflectance properties. The star is made out of glass that, depending on the viewing angle, is either semi-transparent or anisotropically reflective. Reflectance models such as this one are clearly very difficult, if not impossible, to model analytically. Although surface light fields have many desirable properties, they also have several drawbacks. They are generally very large and therefore costly and difficult to render. Light field maps, on the other hand, are small and easy to visualize. Here is a scene which combines real and synthetic light fields that total approximately 20 gigabytes of raw radiance data. Light field map representation of this scene is rendered here at 15 frames per second on a GeForce 3 card using 2 GHz Pentium 4 processor. The discrete surface light field for a triangle can be represented as a 2D matrix where each column of the matrix encodes the appearance of this triangle for a fixed viewing direction and each row of the matrix encodes the appearance for a specific triangle pixel for different viewing directions. Light field maps are a result of the factorization of the light field matrix into a sum of outer products of vectors. The first term of the decomposition represents a constant vector subtracted from the matrix, and the vectors g and h represent the factors of the light field matrix after the subtraction. In practice, just a few summation terms provide a close approximation of the original data. More importantly, since the constant vector and the g's and h's can be represented as two-dimensional texture maps, this sum can be evaluated very efficiently using multi-texturing graphics hardware. Unfortunately, by factorizing each triangle light field matrix independently, we introduce discontinuities at the edges of the triangles. To eliminate the discontinuity across triangles, instead of doing a triangle-centered decomposition, we perform a vertex-centered decomposition. To this end, for each vertex, we construct a light field matrix by concatenating the light field matrices of the ring of triangles around it. We then use the factorization of the vertex matrices to render the triangle light fields. Each triangle light field is now a linear blend of its three vertex light fields. This video segment shows a side-by-side comparison between three-term triangle-based and three-term vertex-based approximations. This sequence illustrates the impact of using multiple terms in the surface light field approximations. Clearly, the difference between the zero-term and the one-term approximations is very noticeable, but the additional terms lead to only minor adjustments in rendering quality. For most models, one-term vertex-based light field mapping produces sufficiently good results. This sequence compares the approximation quality of the two types of matrix factorizations described in the paper. Both produce similar visual quality, but NMF approximation is easier and faster to render. This sequence shows the effects of applying different compression techniques to light field maps. The examples include vector quantization, OpenGL hardware texture compression called S3TC, and the combination of these two. Here is the same sequence of compression techniques applied to the star model. Note that the light field decomposition alone compresses the raw light field data by up to 2 orders of magnitude. Further compression of light field maps through techniques shown here increases the compression ratio by another 2 orders of magnitude.